Okay, so I welcome all of you again to this class of thermal engineering, MEC551. So today's class will be devoted to only tutorials. Okay, so tutorial basically on air conditioning application. Okay, so we will see the use of the psychometric chart in solving questions related to air conditioning application. Okay, so one thing we need to know is that in air conditioning application, I've told you we have one diagram called psychometric chart. So this psychometric chart is designed for pressures only at 1 atmospheric pressure. See, let me show you. So before I start solving the question, this psychometric chart normally is designed for air conditioning application related to 1 atmospheric pressure. So we have the atmospheric 1 bar, 101.325 kilopascal. Any pressure apart from this pressure, then we cannot use the psychometric chart. So it means that when you are dealing with air conditioning, where the given pressure in the air condition is 100 kilopascal, then you are not allowed to use, you cannot use this psychometric chart to find the properties of the air. Okay? Only when the properties of the air is exactly 101.32 kilopascal, 325 kilopascal, or 1 atm. Okay, so under that condition, you are allowed to use the psychometric chart to solve any air conditioning question. So the question that we are going to discuss now, let's see, yes, here is it. So we are told that we have a 5 by 5 by 3 meter room contains the air at 25 degrees Celsius and 100 kilopascal. So 100 kilopascal means this is a pressure. You cannot assume that this is atmospheric pressure. This is a pressure below atmospheric pressure. So we are not allowed to use the psychometric chart. Here we need to use the calculation or numerical method. And I'm going to show you how we have to go about this. So let's sketch the features of the room. Okay, so we have a room in which the volume of that room is given by 5 times 5 times 5 times 3. That gives us how much? 75 meters cube. Okay, that's the volume occupied by the room. And the temperature in the room equals to 25 degrees Celsius. And the pressure in the room equals to P equals to 100 kilopascal. And finally, the relative humidity, Phi, relative humidity in the room is equivalent to 75%. So we want to determine the partial pressure of the dry air. Okay, and then the specific humidity, okay, of the air, and then the enthalpy per unit mass of the dry air. Okay, so if let's say this were to be under atmospheric condition, then we could have just simply take the dry bulb temperature, which is this, and then the relative humidity, which is this, and carefully we will go to the psychometric chart, and then we will read the specific humidity, we can read the density over there. Okay, so these parameters can easily be read. But since the working pressure is a pressure which is different from atmospheric pressure, then we need to resort to the calculation method. All right? So now we want to determine the partial pressure of the dry air. And I've told you, now let's say, again, this is the house. Okay. So the total pressure equals to 100 kilopascal. And I've told you, every atmospheric air consists of partial pressure of dry air component and partial pressure of what? Water vapor, which is the moisture. Okay, so it means that the total pressure over here in the room will be equal to pressure exerted by the dry air component plus the pressure exerted by the water vapor. Okay, so it is this P partial pressure of the dry air that we are interested in. Okay, so we want to find PA. PA. PA is what we are interested in. So, but we know the total pressure. Total pressure is 100 kilopascal. So now we need to find PV. So how do we define PV? We know by definition that relative humidity, okay, equals to what? MV divided by mg. And this is also can be written as PV divided by PG. Okay, so the first equation, this one, cannot help us because we don't know the mass of the water vapor, neither do we know the mass of the water vapor at the saturated state. Okay, be careful over here. So PV is the partial pressure of the water vapor that is present in the air. And PG is the partial pressure of the water vapor at the saturated state. So let me make it clear again like this, that if I have a system, okay, so I have a control mass system or a container like this, and this container contains atmospheric air. Atmospheric air. This is just a recapture of what I mentioned last time. Now, this atmospheric air consists of, let's say, dry air component. Let's say this is the dry air component whose partial pressure is given by PA. Now, if the mass of the water vapor so if the mass, so let's say the amount of water vapor that is present is given by MV at pressure, which is given by PV. Now, if I introduce moisture is the same as water into this system, which parameter is going to increase? MV is going to increase, consequently, PV is going to increase. But PA, MA will remain the same. They will not change. Mass of dry air will remain the same. It will never change. So if you continue to give more fluid into this system, you are giving more water vapor or more water, let's say, assuming we are humidification process. So this MV will continue until when the water or when the system reaches its saturated state. Saturation. What is saturation? Saturation is the condition where this system can no longer hold the water. It means any additional water which you add to it, you start seeing some droplets. Okay, so at the saturated state, then the mass of the water vapor, we are going to call it mg. mg. It's no more mv. Be very careful. Similarly, the partial pressure of the water vapor will be pg. You understand? But the ma remains the same. I've told you the dry air component is not affected in any case. So MAPA remains the same. PA, MA does not change. You understand me? So now, by definition, relative humidity is defined as the ratio of MV before the saturation divided by mg after the saturation. This is what we define as relative humidity. And we can also define it in terms of the partial pressure exerted by the water vapor, which is PV divided by what? The partial pressure at the saturated state, which is given by PG. Okay, so the question we have at hand is related to this. So now we need to define, and I've told you this equation can help us, but the mass cannot help us. Okay, so by definition, we know phi, or relative humidity, equals to PV divided by PG. So by definition, PV equals to phi times PG. Okay, so what is PG? PG is the partial pressure. So PG equals to saturation, P saturation at the given temperature. At a given temperature. So the given temperature related to this question, the dry bulb temperature is 25 degrees Celsius. Okay. So now we need to find PG equals to P saturation at 25 degrees Celsius. And this gives me, if you calculate this carefully, you're going to get PG equals to about, if you check from your property table, okay, you get about 3.1698 kilopascal. Okay, so this gives me 3.1698 kilopascal. Okay, so now we can substitute into this equation. And so now my PV equals to, I know my phi, this is 0.75 times PG, 3.1698 kilopascal kPa. So this gives me eventually 2.3938 kilopascal. Okay, so that is it. And for the partial pressure for the water vapor. So now, knowing this, we can easily calculate the partial pressure of the dry air, because we are told that total pressure P equals to PA plus PV. So it means that PA equals to P minus PV. So this gives me 100 minus 2.38 kilopascal. So if you calculate this carefully, then you will be getting 90 something kilopascal. So that gives us 97.62. So this equals to 97.62 kPa. Okay. So now the next question is to find the specific humidity. See, we want to determine the specific humidity. So specific humidity generally is defined as you can use this equation very easy. Omega equals to 0.622 PV divided by P minus PV. All right. So with this in mind, we will have 0.622 times PV, which is 2.38 kilopascal, all divided by 100 minus 2.38. Okay, so if you calculate this carefully, you will get 0. And this gives me omega equals to 0.0152 kilogram. Sorry. So kilogram of water vapor. Okay, so we normally express it in kilogram of, whenever you see V, kilogram of water vapor per kilogram of dry air. Okay, so V is for water vapor, A is for dry air. So that is the unit. All right, so now the enthalpy of the air per unit mass of dry air. So by definition, what is the enthalpy? Classical definition for enthalpy of atmospheric air equals to H equals to HA plus omega Hg. Okay, so HA is the enthalpy of the dry air component, omega is that's the specific humidity, and Hg is the enthalpy at the saturated liquid state, sorry, saturated vapor state. Okay, so clearly we can have, I've told you, since the dry air component is what we call it, it's an ideal gas. I've told you for all ideal gases, H equals to Cp times temperature. Okay, so means we can express this equals to HA equals to Cp times the temperature, right? And similarly, we have this. Oh, so I think first, initially, let me change this to HV first. So we will come to Hg later on. So this should be HV. Okay, so that's the water and the enthalpy of the water vapor. Okay, so where this can be approximated to Cp times temperature plus omega times what? Hg. All right. Okay. So now there are two options for determining Hg. Either you read directly from the property table, or you can use calculation. Okay, so there is a general equation for it. So either you read, if you calculate Hg at, let's say, 25, or I'll give the general equation for Hg. So Hg is generally defined as 2500.9 plus 1.8 T. Okay, so this is the general equation for how to determine Hg. So either you use this equation, or you go to the property table, or you use this, or you use property table and say Hg at the given temperature equals to the enthalpy at that particular temperature. So this gives us Hg Hg at 25 degrees Celsius. If you determine that both of them is going to be the same, okay? And from the property table, we have Hg equals to 256.5 kilojoules per kilogram. That's from the property table. All right. And if you calculate, so you are going to substitute Hg equals to 200, that gives me so 2500.9 plus 1.8 temperature. The temperature given in the question is how much? 25. So times 25 degrees Celsius. So if you calculate this, you'll get Hg equals to, let's see over here. Yes, 2546.4. Okay, so 0.4. So 0.4 kilojoules per kilogram. So you discover what is the difference? Only 0.1. So it's very, very small. The difference is very, very small. So having calculated Hg and then knowing W already, so we can only easily calculate the enthalpy. So now our enthalpy of the air now gives us Cp is 1.005 kilojoules per kilogram, kilojoules per kg, okay, per degree Celsius, and then times 25 degrees Celsius, all right, and then plus, again, omega we have calculated to be equal to 0.015, okay, times 2546.5 kilojoules per what? Kilogram, kilojoules. Kilojoules per kilogram. All right, so now this gives us the enthalpy now equals to so this gives me 63.8 kilojoules per kilogram of dry air. Okay, so now let's proceed carefully. Now we want to determine the mass of dry air and water vapor. So this is the question: determine mass of dry air and mass of water vapor present. All right, so now how do we determine first? Let's say we want to determine the mass of dry air. Since we know that the dry air is an ideal gas, so we can use, so since dry air is an ideal gas, okay, so dry air is ideal gas. So it implies that PV equals to MRT for ideal gas. So now we are going to use the partial pressure exerted by, let us recapture again the situation in the house or in the room. We have the room like this. Okay, so the room has a certain pressure PA, mass of dry air MA. Okay, the temperature is T. Okay, so and then it has also water vapor PV, mass of water vapor MV. Okay, so if we consider the dry air component alone, now one thing you need to know is that the total volume occupied by the dry air should be equal to the total volume occupied by the water vapor, and this should be equal to V. You understand me? So the room in which you are occupying now, let's say, for example, you are staying at home in your study. Now, the air in your study comprises of two components. One, water vapor component, and then also it contains dry air. Now, the volume, if you calculate the volume of your room, okay, the volume occupied by the dry air component is the same as the volume occupied by the water vapor. So there is no change. Just like the temperature of the water vapor present in the room will be the same temperature of the dry air component. It's just like you bring a thermometer into your house and then you read the thermometer. Thermometer reads maybe 32 degrees Celsius, or let's say 37 degrees Celsius. So it means that's the temperature for both dry air component and then the water vapor. All right, so now let's proceed. So here we can clearly define that PA, okay, times V equals to MA RA. Yes, the ideal gas constant for air, dry air, is different from that of water. Okay, so MA now gives me PA times V divided by RA times temperature. So this gives me 97. Partial pressure for the dry air is 97.62. All right, so kilopascal times 75 meter cube, that's the volume, all divided by, we have 0.287. Okay, so kilopascal per meter cube. Okay, so, oh, sorry, so make a mistake over here. So 287 kilopascal per meter, times meter cube per kilogram per Kelvin times 2029 29 so we have 298 Kelvin. So this gives me 85.61 kilogram. So that is the mass of the dry air component. Okay, so now the easiest way to find the mass of the water vapor is to use this equation. Okay, so let's see over here. So we can have, we know the definition for omega. So omega equals to that gives us mv divided by ma. So if I'm looking for ma, oh, so we will have mv equals to omega times ma. So we know omega already, we know ma. So you can easily calculate mv. All right, so that gives us mv equals to 0.0152 times 85.61. Okay, so eventually this gives me 1.30 kilogram. Okay, so that's the mass of the water vapor that is present in the air. So if you compare the mass of the water vapor, which is given, see, this is about 1.3 kilogram. And if you compare that to the mass of the dry air, okay, so it's very, very, very small. The mass of the dry air is very, very, very small compared with that of the water vapor. Okay, so, oh, sorry, and the mass of the water vapor is very, very small compared with the mass of the dry air. So mass of dry air that we got equals to 85.61 kilogram. Okay, so I will solve another question. I'll move on to another question. Yes, so you can try to do this question if you go home. Okay, so this question says that dry air, okay, dry air and wet bulb temperatures of atmospheric air at 101.325 kilopascal pressure are measured with a sling psychrometer determined to be 25 degrees Celsius and 15 degrees Celsius respectively. Now determine the relative specific humidity, relative humidity, and then the enthalpy. So a question like this, we are giving, you see, the working pressure of the air conditioning system is atmospheric pressure. So we can easily use the psychometric chart to determine specific humidity, to determine relative humidity, and determine the enthalpy. Given that we have the dry bulb temperature and wet bulb temperature. So cleverly, you need to go to the psychometric chart. Yes. So we have on the psychometric chart 25 degrees Celsius and 15 degrees Celsius. Okay, so on the dry bulb temperature, we have 25 degrees Celsius, and wet bulb temperature, see, is 10 degrees Celsius. The wet bulb temperature starts from here. This is 25 wet bulb temperature. Okay, then it decreases if you go like this downwards, and this is 20 wet bulb temperature. Okay, so, and then let's see, we are talking about, how much is that? Yes, 15 degrees wet bulb temperature. So this is 15. 15 is this. It is this line. Goes continuously to this line. Okay, that is 15. So we'll move our line vertically upwards like this. Okay, so from here, you can easily move your ruler to the right, and from here, you can read the omega. Okay, so omega over here is about, let's say this is 4, and 5, 6, about 6.2. Okay, omega will be about 6.2 grams. Be careful, it is gram. So grams of water vapor per grams of dry air. But we need to change into kilogram. So we have to divide by 1,000. So omega gives me 0.0062 kilogram of dry air per kilogram of, kilogram of water vapor. Kilogram of water vapor per kilogram of dry air. So omega gives me 0.0062 kilogram of water vapor per kilogram of dry air. Okay, so now if you need to determine the relative humidity, you see, these are lines of constant relative humidity. This is 100, 90, 80, 70, and we have 60, we have 50, 40. So it continues to decrease all the way. So over here, you discover one thing, that our relative humidity is between 40 and 30. Okay, so I'll take approximately 35%. So relative humidity is about 0.35, which is equals to 35%. Okay, and then we need to determine also the enthalpy. So now let's see, where do we have enthalpy? This is the enthalpy. Okay. So the enthalpy is this. These are lines of constant enthalpy. Okay. So we have, this is 20, 30, 40, 50, and so on and so forth. Okay. So if we rule our line cleverly towards this section, our enthalpy is going to about 42. 42. Okay. 42. that is specific enthalpy. H is about, H equals to 42, okay, kilojoules per kilogram of dry air. Okay, so this is very easy question. So you can try your hand on this if you go home. Here in this case, we are given temperature and relative humidity. Okay. So next question, let's see. I'll move to the next one. Yes, let's discuss this question. Pay attention carefully to this particular one. Here, again, we are told that air enters a 40 centimeter duct. Okay, 40 centimeter duct. Let's see over here. So let's come in and wait. Okay. So here we have the air conditioned duct. Let us sketch it. Okay, so this is the air conditioned duct. Okay, so air enters at 40 centimeter diameter cooling section. Cooling section means that heat is being taken out. We have Q out, okay, of 1 atm. Better maybe I should sketch it outside. Okay, so we have a cooling section. So this means Q, we have Q out. So we have Q out. This is state 1, and this is state 2. The air is entering at this state. Okay, and we are told that now the diameter of the duct is given. This is the diameter. The diameter of the duct is given. And what is this diameter? D equals to 40 centimeters. 40 centimeters. So in meters, this gives us 0. We divide by 100, 0.4 meters. And now the pressure, existing pressure of the system is such that it is 1 atmospheric pressure. So we can easily use the psychometric chart, okay, for this without resorting to any calculation. Now, the air enters at 30 degrees Celsius and 32 degrees Celsius and 30 relative humidity. Okay, then the velocity is also given. So we have the temperature at the inlet, T1 equals to 32 degrees Celsius, relative humidity equals to 30%, which equals to 0.3. And then the velocity, V1. Velocity, the velocity equals to 8. So velocity V1 equals to 8 meters per second. Okay. So now the Q out is giving us as well. So Q out, we are told, equals to 1,200 kilojoules per minute. Okay. Now we need to determine the temperature, the exit relative humidity, and then the exit velocity. Okay, so T2, okay, this is not given, and then V2. Sorry. Also, we need to determine. Yes, so first thing, you see, since the pressure, the working pressure over here, pressure equals to 1 atmospheric pressure. So this implies we can use psychrometric chart. Psychrometric chart. Any pressure apart from this, you are not allowed to use psychrometric chart. So since we are looking for the properties at this particular state, we need to identify two properties. We need to identify two properties such a way that these properties will help us to identify all other properties. For example, let's say if we know, and let's say for a cooling process, let us draw the schematic diagram of the psychrometric chart. Okay, so this is, remember, this is a cooling section. So it means temperature is reducing. Temperature is reducing like this, from state 1 up to state 2. You understand me? So temperature is going down. Now, so this tells us that the omega over here, since omega 1 equals to omega 2, if we are able to determine the omega at state 1 with the help of the temperature and then the relative humidity, then we can find the omega at state 2. Okay? So then if we are able to determine also that with the aid of this Q out, we can find the enthalpy at state 2. Okay? So we can find H2. If we are able to determine H2 with these two information, we can determine all other properties. Okay? So first thing is to find omega 2. Okay? So we move to the psychrometric chart at state 1. At state 1, what information do we have? At state 1, we know T1 equals to 32 degrees Celsius. And then V1 equals to, the velocity cannot help us. Okay, so only the temperature and the relative humidity we are going to use. So we have relative humidity equals to 30%. So with this, we will move to the psychrometric chart, and then we will determine the enthalpy. So we find H1 from the chart equals to 55 kilojoules per kilogram. Okay, omega 1 also, this gives me 0.008 okay, 9 kilojoules, sorry, kilogram. So this gives us kilogram of moisture per kilogram of water vapor. And note that omega 1 is the same as omega 2. All right? So then the specific volume also. The specific volume at state 1, V1 gives me 0.877 meter cube per kilogram of dry air. All right? So now, with this, let's recapture again. We are interested in the exit temperature. So first thing, we want to determine the relative humidity. Oh, sorry, the specific humidity at state 2. Okay, so we have determined that. Okay, now we need to find, excuse me 1 minute. Yes, so now we need to determine omega, we have already determined omega 2. Now, the next thing to find is determine H2. How do we determine H2? Now, we have to consider the energy balance. Consider energy balance. If you consider the energy balance of the system, let us have a sketch of it again. I have my sketch over here. This is a cooling system. I have my Q out over here. And I have this is state 1. This is state 2. I have the fluid flowing inside, air coming outside. Mass flow rate of the dry air component here is M1. The enthalpy of the air over here is H1. Mass flow rate of the dry air component here is H2. Enthalpy here is H2. So this gives us the energy of the air that is flowing in. And the energy of the air that is flowing out is given by this. Okay, E2. So from energy balance, we have total energy in, okay, should be equal to total energy at the outlet. So we have here E1 is going in, and Q, watch out carefully, Q out is leaving. So we are taking some heat out of the system. So we have Q out plus E2. This is also leaving the system. So eventually we will have, if I substitute E1 and E2 into the equation, so the parameters for it, we will have Q out, okay, equals to E1 minus E2. Okay, so this gives me mass flow rate of the dry air component, MA1, H1, okay, minus MA2, H2. All right? Be careful over here. You see, the mass of the dry air component, MA1, is the same as mass of dry air component MA2. Because dry air component does not change. Same. Okay, so we'll have over here MA1, MA1 equals to MA2, and this equals to MA. So eventually we'll have Q out equals to MA into bracket H1 minus H2. So we need to determine anyhow MA. So how do we determine MA? MA equals to, let's say MA1 equals to the volume flow rate, okay, or it is given by the velocity of the fluid divided by the specific volume. Okay, so this gives us velocity V1 divided by specific volume times the area of the duct A1. All right. So we have the velocity at the numerator part times the area divided by the specific volume. Okay, so this gives us the mass flow rate. All right, so let's move on. So we know the velocity at state 1. What is it? So the velocity is 18 meters per second. So we have 18 meters per second times the area. So the area is pi d squared. So pi d, 0 point, diameter is 4 squared. Okay, so meters squared, all divided by specific volume, V1. So we know the specific volume already, so that gives us 0.877 meter cubed per kg. All right, so now eventually we will have mass flow rate equals to, of the dry air equals to 2.58 kilogram per second. Right? So now we can easily determine our H2. Okay, because we know, okay, we know Q out equals to MA H1 minus H2. Okay, so from this equation. So, but what is our Q out is given already. So we have 120 kilojoules per minute. We express per second, so divided by 60 seconds or 60 kilojoules per second. Sorry, it should be like this instead. So it should be 1200 divided by 60 kilojoules per second. This gives me 2.58 kilogram per second into bracket. H1 we know already. Okay, so H1 is 55. Okay, so 55 minus H2. So from here, I can easily determine H2. So H2 equals to 47.2 kilojoules per kilogram. All right. So now I know two important parameters, namely the enthalpy and the omega. Okay, so now at state 2, H2 equals to 47.2 kilojoules per kilogram of dry air. and omega 2 equals to 0 point, and what was it? Let's see. Yes, so 0.0089. 0.000089. So kilogram of moisture per kilogram of dry air. So with these two properties, we can find T2, we can find relative humidity at state 2, we can find specific volume at state 2. You understand? So now T2, if you read carefully, this gives me 24.4 degrees Celsius, and relative humidity 46.6%, and specific volume 0.856, okay, meter cube per kilogram of dry air. Okay, so this, now we need to find the velocity at state 2. So velocity at state 2, let me see. So the velocity at state 2 by definition is given by V2, okay? So V2 equals 2, and that gives me the velocity, okay, or let's say the mass flow rate, the mass flow rate, we should use instead mass flow rate at state 1 equals to mass flow rate at state 2, and this equals to V2, okay, divided by specific volume at state 2 times the area. Okay, so the area is the same because the cross-sectional area, because the same diameter, the diameter is the same. So area A1 is the same as A2. You understand? So A1 and A2 are the same. So now from here we can determine velocity V2. So V2 now gives me mass flow rate times specific volume V2, okay, divided by the area. Okay, so let's see over here, divided by the area. Okay, so if you calculate this carefully, we will have, let's see over here, and this gives me so we will have 0.856 times 18 divided by 0.877. So now the exit velocity is about 17.6 meters per second. Okay, so that is it for this particular question. Okay, so let me see, maybe we can attend to another one more question. Let's see. Yes, so maybe let us look at this particular question. Okay. So the question says that an air condition, okay, system operates on total pressure of, so again here we have 1 atmospheric pressure. Okay. Sorry. So we have total pressure. So an air conditioning system operates on a total pressure of 1 atmospheric and consists of heating section and humidifier that supplies wet steam. Okay, so maybe let us sketch the system over here. It consists of a heating section and humidifying section. We have, okay, so first, this is our heating section. Means there is heating, means we have Q in. Okay, be very careful. Okay, that supplies wet steam. So, and humidifying section. So this is the humidifier. So humidifier means we are increasing the amount of water vapor in the humidifier. Like this. Okay, so water enters in this. Okay, so this is the humidification. Okay, now the temperature of the humidifier, that is, we have water. Okay, saturated vapor. In other words, this is saturated vapor. Okay, source temperature equals to 100 degrees Celsius. All right, and then air enters the heating section. So let's say this is state 1, and then we have state 2, and we have state 3. So it means T1 equals to 10 degrees Celsius, relative humidity 70% at a rate, volume flow rate. So volume flow rate V1 equals to 30 meter cubed per minute, and leaves the humidifying section. So it means state 3. This is the humidifying section. So it leaves the humidifying section at, so it means T3 equals to 20 degrees Celsius, relative humidity 3 equals to 60%. Determine the temperature and relative humidity of air when it leaves the heating section. So T2, we don't know, and relative humidity 2, also we don't know. So we want to determine this. So one thing that needs to come to your mind, first thing is that if you want to find T2 and relative humidity as state 2, since this is a simple heating, so for a simple heating, omega 1 is the same as omega 2. Okay, then we need to identify another property which is going to help us to determine the temperature T2 and relative humidity T2. Okay, so first, let us list down all the properties at state 2, sorry, state 1. So at state 1, we have, at state 1, given properties, temperature is given, T1 equals to 10 degrees Celsius, P1 equals to 70%. So from these two information, you can get H1 equals to 23.5, okay, kilojoules per kilogram. And then omega 1 equals to 0.0053 kilogram of water vapor per kilogram of dry air. And specific volume, okay, from the psychometric chart, 0.809 meter cube per kilogram, okay, of dry air. All right. Similarly, we can determine, yes, so let us see, we are interested in the properties at state 2, namely T2 and the relative humidity at state 2. Okay, so clearly what we need to do is to determine first mass flow rate. Okay, so the mass flow rate at state 1 is the same as mass flow rate at state 2. That is the mass flow rate of the dry air component. That's what I mean. Okay, so we will have a situation like this. Mass flow rate of dry air component at state 1 equals to MA, 2 equals to MA, 3. And this gives me the volume flow rate at state 1 divided by specific volume at state 1. So this gives me 35 meter cube per minute, all divided by 0.809 meter cube per kilogram. So mass flow rate of dry air now, MA equals to 43.3 kilogram of dry air. All right. So now we have to determine the energy balance on the humidifying section. Okay, so because of the fact that, you see, if we have to find, we know we have large information about the exit point and then the humidifier. So this can help us to determine the enthalpy at state 2. Okay, so because we know omega 1 equals to omega 2, but how do we determine H2? H2, we cannot use Q in. Q in, we don't know. If we know Q in, then we will just proceed like this, that Q in equals to, we will proceed like this, that Q in equals to mass flow rate of dry air, H1 minus H2. But we don't know Q in. Q in is not known. So we cannot use this equation. So it means we need to move somehow to the humidifying section. Find the energy balance, okay, on the humidifying section. Okay, so consider the humidifying section. Consider, or let's move on to the next. So consider humidifying section. So we have water is coming, steam is coming in. This is state 2. This is state 3. Okay, so here we have energy at state 2 is this. The energy at state 3 is also this. Okay, and then the energy of the water at this particular state is given by, let's say this is EW, the energy of the flowing fluid. All right. So, and this gives us, we will have, as far as this equation is concerned, we will have, let's see, mass flow rate. Okay, so total energy in equals to total energy at the outlet. So what is the total energy in? We have E2 plus that of the water, energy carried by the water. This should be equal to energy for the air which is leaving after the humidifier. Okay, but what is this E2, E3, and the EW? So E2 equals to mass flow rate of dry air times H2. E3, mass flow rate of dry air, okay, H3. EW equals to mass flow rate of the water times enthalpy of the water. Okay, so that's the enthalpy of the water. Okay, so now we will have a situation like this. Let's see. So if I substitute all this into the equation, I will have Ma2H2 plus MW HW, okay, equals to Ma3H3. Okay. If you go back to the definition for the mass balance for water, okay, in the previous section, let's see, mass balance for water. Yes, so let's see over here. Yes, MF equals to mass flow rate of dry air, omega 2 minus omega 3, minus omega 1. Okay, so, and let's see over here, we can have, so I hope you understand how this equation came about. Because here we are saying, if you want to establish the mass balance, okay, so, and let's say for the water which is flowing inside this tube, okay, inside this tube. So we can express it. For the mass flow rate of the dry air component is the same. But for the water, we have MW1 equals to MF plus MW2. So, but what is this MW1? Okay, it is defined in terms of, so omega, where omega equals to MV 1 divided by MA1. Okay, so that is it. So then we can have MV1 equals to omega 1 times MA1. Okay, so like this. So the same thing where we can represent MW by the MV. Okay, so here MV1 is the same as MW1. Okay, so the same thing we are going to adopt over here. Okay, so let's see. Yes, so we will have a situation like this. MW, so we will have like this, let's say MW, or let's see over here. So if we want to make a substitution for this MW, let's see. Okay, so we have the humidifier over here. This is the mass flow rate of the water. And then here we have MV2. Here we have MV3. So MV2 plus mass flow rate of water should be equal to MV3. Okay, so that's MW, and MW now equals to MV3 minus MV2. But what is MV? So this MV, we know by definition omega 1 equals to MV1 divided by MA1. So whenever we see MV, we replace by omega n MA. So this gives me MA3 omega 3 minus MA2 omega 2. Okay. So now, carefully, we will know that if we substitute that into the main equation, we have Ma2H2. Okay, so this gives us Ma. So Ma2 H2 plus, and this now gives me, I'll have Ma3 omega 3. So Ma3 omega 3 minus Ma2 omega 2 all times H times what? HW. So HW. This gives me Ma3 times H3. So but Ma1 equals to Ma2, which equals to Ma equals to Ma. Okay, 3, which is equal to, again, which equals to Ma. Okay, so wherever we see this, will represent Ma is going to virtually cancel all out. So Ma will cancel here, Ma will cancel Ma, and Ma. So we have H2, okay, plus omega 3 minus omega 2, all into bracket, HW equals to H3. H3. So that is it for this derivation of the energy for the mass balance. So from here, we are interested in H2. So H2 gives me, let me see, gives me H3 minus omega 3 minus omega 2 into bracket HW. Okay, so we can easily determine the properties at state 3. Okay, at state 3, okay, so we know the temperature at state 3 is giving T3 equals to 20 degrees Celsius, Phi3 equals to 60%. So from here we can determine H3 equals to 42.3, and omega 3 similarly equals to 0.0087 kilogram of moisture per kilogram of dry air. So we can easily substitute into this equation. Okay, so since the water, let's say, is saturated vapor, so HW equals to Hg at 100 degrees Celsius. And this gives me, carefully from the property table, 2675.6. Okay, kilojoules per kilogram of dry air. So if you know all these things, we can easily substitute into H2. So eventually H2 equals to 42.3 minus into bracket 0.0087 minus 0.0053 times 2675.6. So this gives me 33.2, so 33.2 so 33.2 kilojoules per kilogram. Okay, so from here we can easily determine, we know H2, omega 2 also we know already. So with this two information now, we can easily determine omega 2 is the same as omega 1, which is 0.0053 kilogram of moisture per kilogram of dry air. So with these two information now, our T3 equals to 19.5 from the psychometric chart, and Phi3 equals to 37.8%. Okay, so now the B part, let me see. Let me see. Now the B part, we have to calculate the rate of heat transfer. Q in is equal to mass flow rate H2 minus H1. So this gives me, if you calculate carefully, you substitute all the parameters, you get 42 420 kilojoules per minute. Similarly, mass of water vapor in the humidifying section. So for the C part, mass of water vapor equals to MA omega 3 minus omega 2. So if you calculate this also, this gives you 0.15 kilogram per minute. Okay, so this brings us to the end of this question. Okay, next time we are going to look at situation where the pressure at different pressure, let's say a pressure which is different from atmospheric pressure. For example, if this pressure equals to 95, how are you going to handle this question? So that will be the next discussion, and then we'll move on to the last topic, which is convection. Okay, so let me see if there is any question until now. Is there any question from anybody? So, is there any question so far from anybody? Okay. Is there any question so far? Okay, so now I think we will stop over here, and then we